Hey guys, BBI here. I want to stop and say thanks for tuning in and checking out whatever the video is about that's about ready to come up next. If you could take a minute and hit subscribe, I'd greatly appreciate it. And if you enjoy what you've seen here, make sure to hit the like button. We'd greatly appreciate your support. Anyhow, guys, all that aside, let's get on with the show. Cause it's a beautiful day in the amplifier neighborhood. A beautiful day in the amplifier neighborhood. Could you be mine? Would you be mine? Won't you be my neighbor? Good morning, boys and girls. Today on Amplifier Mr. Rogers Show, we're going to be working on a WorldWide. This is a WorldWide 1x4 with Toshibas in it, iron core transformers. We're just going to come back and revisit it. According to the customer, this thing is working. It's just needing my love. And I'm like, oh. Like, so you want me to put a Mr. Rogers sweater on it, or, you know. He said, just go through it and see what you got. And I see a couple things in here I want to change to try and make it a little bit better. A little bit better. So the first thing I noticed was that the power supply switch, I'm just standing here and looking at it, and I started twiddly dinking around with it, and I realized, oh wow, I started working on it and I'm not videoing it. I better stop. So first thing I noticed is the power switch was incredibly loose on the front. Our on-off switch. Our LEDs are a little bit bunk. I got to come back and push those through. The other thing I noticed was the SSB. It's missing some pots. The other thing is, this has got sideband on it, but there's no bias. So, guess what? It means I get to call the customer back and say, do you need bias? So, we're going to put ourselves a little star lock nut behind the sideband delay switch so we don't have to worry about that ever coming off again in the future. All right, let's swing this camera around and take a look for up the skirt and see what we find. So, I don't know if you guys know this or not. These are really good transformers. They're made in Mexico, right? And what they come out of is APC battery backup units. I have a bunch of these sitting up here that a good friend of mine is stripped out of APC units. I've got the transformer that we could take both of these out and just put one in here. But we're going to work with what we got. It's got 4 matching Toshibas in it, and I don't see any signs of it being burned up or nothing. But I've made it a common practice at this point to get rid of these. This is your standard epoxy submerged bridge rectifier, 50 amp, 50 volt. And this is what they had for decades to work with. It's neat. You go back and you look at the lineage of the rectifying diode, your bridge diode setup, and just one of these units used to be 4 times bigger than this cabinet back in the 50s, right? So when they came up with this design in the 80s, well, first off, let's back up. Before that, the quality of the diode was so low that no matter what, you still had an AC ripple that would take place. So after you would have your DC pop out of this thing, you would have yet second another isolation transformer to help cut that ripple out. Well, in the 80s and 90s, the quality of the diodes went way up, like way up. And that's when we were able to go to this style of submersion, and we were able to go to just a filtering cap without having to have an isolation transformer, which I think is great. But these are, for a minute, these things were really cheap. And they worked well-ish. And if you kept enough heatsink underneath them, they would kind of hold together. I mean, this is living proof. This box is old, as we can tell just by looking at it. But there's better technology out there. After having replaced many of these 50 amp, 50 volt things, by the power of Grayskull. Okay, here we go. I am going to switch it out to my favorite. This is rated at a stupid, dumb voltage, but it works. This is a single phase, 200 amp, 1600 volt continuous bridge. And I've had a lot more success with these lasting. Let me zoom in real close so you guys can get the Chinesium numbers off of it. I've had a lot more luck work with these lasting than those little 50 volt bridges. So when I see them 50 volt bridges, I usually pull them out and I file them in the trash can and I replace them with one of these. It's the easiest thing in the world to install. I had a gentleman call me here a couple weeks ago and I sent him one of these in the mail. His bridges had gone bad, little 50 amp bridgers. And I said, squiggly line equals AC. Of course, positive is positive and negative is negative. So all you got to do on these is you sum your transformers here, here, here. And then you take your positive lead, run it to your cap, your negative lead, and run it to the cap or run it to the ground. And it'll fit approximately in the same position over here as these guys. But I don't trust these for nothing. These 50 amp, 50 volters. I don't trust them for anything. This box is a really, really clean build. And so your eyes aren't playing tricks on you. There's actually another winding in this combiner. So it's your standard 2-to-1. And the other thing we're going to do is we're going to remove this old cap. These things have a tendency to fail when they get hot. And let's face it, the cooling on these things isn't the best in the world. So we're going to replace that with a metal capacitor. We're going to upgrade the power wires in it, of course. See if we can squeak a little bit more out of her. But the whole idea is to make this thing run for another 20 years. Which it's been running from probably the 90s till now. We're going to block off our vent over here. So we're going to force all of our air through our cabinet for better cooling. And we're just going to check our tune. But this thing is running good. Now, like I said, he told me it was running good. So now what we got to do is we got to verify that process. So we'll bring it up slowly on a variac, because we all know that it is absolutely suicide just to plug this thing in and flip the switch. This is an unknown, and I could be creating more problems for myself by doing that. So here in a minute, we'll bust the variac out, and we'll slowly turn it on, and we'll watch our voltages, and we're going to check for a leak across the diodes for AC ripple. Then I got to see if I need to add bias to it or not. These little caps, these Semic caps, or not Semic, what is it? Yeah, Semic. Where's the Seco? No, Semic. Yeah, Semic. Also made by Cornell Doubler. These are very hard to find. I mean, there's good parts in this amplifier. It's the reason that it's run for as long as it has. But I have a hard time buying that somebody sent me this amplifier just so I could go in and redo the power wires on the inside of it and see if we can squeak a couple more watts out of it. There's got to be something wrong. This thing's been sitting here, oh God, 18 months now. So I want to verify as I turn it on. So let's go grab the variac and let's turn this thing on real slow together. Hmm, interesting. 1 volt, 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 1 volt much better. Okay, so let's see what we get. Variac hooked up. Voltmeter, obviously, hooked up, and we're directly to the bridge. Let's take off the old wedding ring. Let's turn on our Variac, and we'll slowly start bringing our voltage on here. I don't feel it fighting my fingers as I turn the knob on the Variac. So we're 4 volts, 5 volts, 6 volts, 85 volts, 90 volts. Okay, we're at 110 volts on the input, floating to 18.6 volts. No leaking. So what I basically did is I turned this thing on slow because I don't trust the caps and I don't trust the diodes. But this is a good sign. Okay. This is volts DC, which we can clearly see. So we're sitting at 18.45. Now we're going to go to volts AC, which we can clearly see. And if the capacitor was leaking, as in not physically leaking its shmoo out of its internal guts, like a Tijuana hooker on a Saturday night, if it was leaking AC through, it would show up as a voltage on the AC side. Now it could still show up once we put the power supply underneath a load. So there's a different way that we do that, and we look for that with the oscilloscope and the RF. You can see you have your signal band, you just throw a carrier, and above and below just your constant carrier, if there is, well, there's little tiny squiggly lines that will be perceptible on the outside of the carrier from the AC ripple in the power supply. But I don't think we're going to see that. Well, I guess the next step is to actually hook it up and run it and see what we've got as a baseline. So let's see how quickly our voltage bleeds off here. Are none of our LEDs working? None of our display LEDs are working. Interesting. That's tied directly to the hot. So these green LEDs, this one, and this one should all be on. And they are not doing shit. Okay. I got volts here. I do. Interesting. How's that wired? Oh, there's no ground. That'll do it. I'll do it every time. It's interesting. There we go. Okay. Now we're getting depletion. Now our lights are working. So at least we know the cap is stiff. Down we go. All right, I'm gonna go fix our LED issue. We'll get the Variac out of line. We'll hook it up to its. I have a 110 outlet that is 15 amps all to itself. Not all the shop lights and computers and all this shit are all drinking off. This is its own separate line. So I'll get that dug out, get this thing hooked up, and we'll give it a run for here. We'll see what happens. So we got 1,000 watt slug in peak, 1,000 in average, and our 5 watt slug in reverse back from our Bird 10,000 watt dummy load. We've got our voltage probed directly to the bridge. Put this in standby. There's our 15 or 20 watts worth of drive. Let's put this thing into operate. 15 volts, it should be doing a lot better than that. Let's zoom on in here for a second. About 900 is what we're getting out of this. So there's a couple things that are limiting us here. One is our pill. It's a 2290 driving 4 2879s. Now, that's good because that puts us in a position to where we can't overdrive nothing. But if we really wanted to make this sucker scream, get another 200 watts or so out of it, we change out this 2290 and go to a 2879. Okay. Now, this is where I call the customer and ask him if he does sideband, which I doubt he does. Because right here, there we go. Class C. So it might have a sideband delay on it, which all that is an electrolytic, which they have hanging over here on the front end of the cabinet. You see it down in there, right there. That's our sideband delay. This thing is obviously not set up for sideband, so. Okay, let's go ahead and let's do our power wire modifications now that we know it does about 800 to 850 to maybe 900 at the most. Let's put our new rectifier in there and let's see if this helps the situation any at all. It should show a little bit of improvement, maybe 100 watts or so. We'll see. It's like a solder fest pig pen on the inside of this thing. This is all hunks of solder and aluminum, and this all come out of this box. It's just filth that was sitting inside the cabinet. I'm sitting here pulling parts out and I'm like, oh my God, this is horrible. This is the most wild thing in the world right here. Check this out. Turn my viewfinder around here. This is the bottom side of that bridge network. Because we used self-tapping, self-cutting torture devices, this is all underneath the heatsink, or trapped between the heatsink and the rectifiers. Okay, I got to clean up my workspace. I can't. And then I'm going to take this out and I'm going to wash the inside of this because this is dirty. It's just old. Okay, it's dirty. We're going to make it clean and pretty again. And we can do better. We can do better. We can do better. Okay, so we drilled a couple holes through the heatsink here. And then this is like a 1/8 inch hunk of aluminum plate that we're going to put as an extender for our bridge rectifier off the end of the heatsink to help support the bridge rectifier, but also to help carry the heat load. So I put a very nice thin coat of thermal compound on the plate and also on the heatsink. Now, This is our bridge, and we've got a very copious amount of heatsink compound already on the supporting structure plate. So when I did the dry fit on this, it's going to be a little bit tight. So we'll see if we can get this to go for us here. There's one. Sweet. Okay, that's two. This will not help us do hardly any more power. What this brings to us is a newer bridge with a little bit more reliability to it. Well, actually a lot more reliability to it. And the other thing it does is it helps support this whole side of the heatsink, because up until now it was just being held up by the phenolic. So, now let's come around from the backside. We'll torque the backside down here. Excuse me. That one started. Hold on. This isn't working for me. There we go. We don't want to get too carried away because we have the potential of bending the rectifier. Normally what I'll do, there's no room for it, we would sneak it down on the cabinet and just bolt this directly to the cabinet body itself. But there's no room for it. So we got to do it this way. Yeah, I'm not going to get this any tighter. Nope. What about you? Okay. And now we know we got good caption on the plate because we're getting schmoo squirting out from all the different orifices all the way around the sides. Just don't want to over torque these ones in the back because they're not the ones doing any physical heat shedding or work. It's our connections up here in the front half. So this whole plate is allowing us to transfer heat to here. So we all know aluminum conducts heat a little bit better than the copper, but the copper allows for more heat density, which is a conversation that we'll have another day. Okay. In short, aluminum is really good at taking heat from a small object, picking that heat up and moving it, okay? Copper is a very good sink, as in it like holds the energy. So if we wanted to use it as like a spreader to take the heat from a small part and spread that heat out over a large surface area versus having it very concentrated, that is the upside. So like, I don't know if you guys ever noticed on the copper mine, I did the copper inserts into the heat sink. Well, the heat that comes off the transistors gets wicked into the copper and then gets spread out across the whole surface area of the copper, and then gets transferred to the heat sink, allowing us to utilize more of the heat sink, which allows us to have better dissipation versus having just a saturated amount of just a couple fins worth of heat. Over time, the heat sink will absorb that energy and spread it out, but it's more efficient to pass it through the copper and then try and dissipate it through aluminum. A little tricky. Okay, long story short, new rectifier's installed and that sucker ain't moving. Okay, now I know every single one of you guys were like, what? Bullshit. Okay, so I just had this conversation with my friend Cooley High the other day. Okay, and he's like, I was sending him pictures because he's asking me about a 32 pill build, and I started sending him pictures. I said, do you want one that's like way over the top like the copper mine, or do you just want just a regular operating 32? And he says to me, he goes, but BBI, we all know that aluminum dissipates heat faster than copper. And I was like, dude, what are you talking about? You're focusing on the wrong thing. And so I very quickly went out and I went and typed into Google, copper heat dissipation advantage over aluminum. Okay, so you got it. There's a give and a take. Quote, aluminum has the ability to absorb heat faster than copper, and when removing from heat source will cool faster because of the less dense material than copper. So aluminum can dissipate heat better when removing it from a source because of its density. But, it says this in big words, but in a system with steady heat input, like a computer, comma, transistor, comma, okay, copper is better to keep heat going into and out of a material, much as with electricity. So you have to visualize that your transistor foot is like you're moving electrons, okay? I mean, you're moving energy, excited molecules. So we all know that if you have a fast moving molecule, really fast, molecules are moving quick, you've got something hot. Well, if you've got molecules are moving slow, it's cold. So that heat energy is yet another form of measurable energy, right? Just like a volt or an amp or a watt. The copper will sink the heat better and dissipate it over a larger surface area. Meanwhile, the aluminum will dissipate the heat down through the fins because of its less dense nature and be able to allow us to utilize more of the heat sink more efficiently, more uniformly. Those are the laws. I'm not making this shit up. It's the truth. So technically, aluminum, because it's less dense, works better as a radiator. From a constant heat source, copper is more efficient at taking that heat energy and dissipating it across a larger area. So there's a give and a take. Okay, so now let's talk about this crazy horseshit. This is where we're going to start picking up a little bit of power. If you are trying to sum transformers together, most of the time you want to do it post-rectification. It's a little bit easier to work with, a little bit. In this particular application, we're going to sum them pre-rectification. This is very important. And it doesn't matter if you're doing switchers, it doesn't matter if you're going to stack transformers. It's very important that your primary leads, your source leads, going to your switchable link source are the same length. That way the equal amount of energy goes to both transformers on the primary side, which is your input side. On your secondary side, it's even more important because the voltage is lower. When we go lower in voltages, you guys, as everybody knows, and listen to me when I say this, I didn't understand any of this shit till I started working with it myself, and I had to have people that were smarter than me explain it to me. Now I have that knowledge and I'm sharing it to you. The voltage is lower, so therefore, i.e. with lower voltage, you're going to have a little bit, higher resistance, okay? So it's really important that things are matched. Do these two leads look matched in length to you? They do not to me. So, the way this was set up before was this transformer came right down and hooked up to the bridges. Boop. And then this one came along in a nice, neat little pattern and hooked up to the other end of the bridges. I say, the way that this should be done, is that these two leads need to be the same length. We sum these together at a larger piece of wire, then we take the larger piece of wire and we go over to our bridge. That way, when we key the mic, bring an electrical load onto our rectifier network, both transformers are seeing the equal amount of current draw across both devices. Because what will happen is if you have this one is closer to the load and this one is farther away, on the secondary side especially, this transformer is going to see 90% of the load and this one's going to see almost nothing. Meaning this transformer is going to get super hot and you're going to see significant voltage drop because this is not doing shit until this thing can't give up any more amperage to the circuit. So we have to sum these things equally. And then from a sum point, then take it to the bridge rectifier. That way the current load can be equally distributed across both transformers. Food for thought. I'm going to do that now. Let's see what I come up with. Okay, BBI, come down off your goddamn soapbox, you bastard. So the more you'll get to know me, the more that you'll find out I absolutely have a disdain for butt crimps or hemispherical compression joints. I know like. I'm not a big fan. So I'm adding a little bit of schmoo to help the glue go together here, because this straight out of Mexico wire isn't the greatest in the world for accepting solder for the most part. Okay. So we're taking two pieces of 12 and we're summing them together on a single piece of 6. Okay, and we're actually doing this. This is actual 600 volt wire. Because remember, at this point we're still playing with AC, but it's not very low AC, but it's still AC. So now what we're going to see if we can do, we're going to start at the bottom, apply heat to the joint, we're going to let the solder through convection and through surface tension wick its way into our joint here. That's plenty hot. The pores of the metal are more than adequately hot to be open to letting the solder flow into them. There we go. There we go. Everything is screaming hot. Our wire jacket's screaming hot. Our wire itself is screaming hot. Now the worst thing that we could do would be to go and seriously move that joint around. So we're going to let it cool down. And when we're done, it's going to look just like this. And then we'll put marine grade epoxy based heat shrink on this. That joint's never coming apart. I don't have to worry about copper fatigue or copper hardening or any of the other little bad things that can take place to cause us to have a weaker joint. But now, electrically, the electrons have to flow the same distance from each transformer. So the electrical load that's presented here, we're now going to be able to fully utilize both transformers. Well, here we go. Okay, so please note our voltage. Just a wee bit higher. So we'll bypass our amp. Same amount of drive as before. Hello, 1 2 1 2. Hello. Now we're sitting up there around 15, 16 volts. Instead of dropping all the way down around 12. So we're able to get more current out of the transformers. So we've seen what? 180 watt, 200 watt improvement. But over here is telling this true story. Now both transformers are working. So all I did was I made it so that our bridge network here is modern, 1. 2, it's actually up to the job. But 3, it's getting fed with equal length wires. And the transformers, their current is summed together at the appropriate place. So everything's going the same distance and has the same load placed upon it. So I'm not a big fan of using the eyelets on these things. I just pull the screws out and I solder directly to the bridge. A lot less loss that way. We used a single piece of 4 gauge to come out. It runs down the length of the heatsink and comes over here to our distribution bus. Then I gave it a small power wire upgrade coming to the transformers, which will help it run just a little bit better. It's more or less about heat. You can run that little 22 gauge wire in the back, and you'll notice that you're going to lose about maybe 10 watts, 15 watts per 2-pill section. But if you measure with a FLIR, or any kind of other thermal imaging device or thermal detection device, you'll find that your transistors are going to run 15 to 20 degrees hotter. It's because they're having to work harder and it pulls more current. So all we're doing is eliminating that little bit of resistance of the little tiny bridgeable link that most guys put in there. This helps a bunch. So gave it the power wire upgrade. Then they had a piece of 22 gauge wire feeding the driver section that come off of here and ran around. Come back to the distribution bar. Now we're running a nice solid big piece of 12 gauge that can easily carry the 20 amps that transistor is going to pull. I had to add a distribution tab over here. You guys can't see at this angle, but I'll show you here in a few minutes. And yeah, bridge is working beautifully. I went and I hand tied all the coax to keep it in place. Because the first thing I noticed when I first opened this is because the wires are all flopping around loose, this ground on the coax, right, all about perspective. This ground right here on the coax was shorting up against, stop it, was shorting up against the input tab here. And so to help prevent that from moving around anymore, we went ahead and hand tied it. We gave it a bath. We cleaned it up. We replaced our input and output combiner resistors. I changed our output resistor to a metal clad stack over here in the corner. And then the other thing I did is I added a new coax connector. The old one was slopped out like the chick that works at the donkey show in Tijuana. It was loose, really loose, to the point where if you didn't have your coax connector screwed down so tight Mary Jesus herself couldn't get in there, it wasn't making contact. So I went ahead and replaced that with a new Teflon, not plastic, because the one that was in there was plastic based. So it's got a brand new Teflon, gold plated center conductor, SO239 connector on it, or PL259 on it, whatever. Played with the input tune. I changed that capacitor right here. And then the other thing I noticed is that the little capacitor over here was a 330, which immediately made me go look at this capacitor here, and it was a 1000, specifically this guy right here. I changed that out to be a more appropriate 820 for a 2290 driver. I took our voltage divider out, which sits here, because all it was doing was generating heat. This does not help us pick up 1 single watt. The theory, the ideology behind that is that it helps reduce the amount of drive going into the 4-pill section. Well, when you've got a single 60 watt transistor hitting 4 Toshibas versus, you know, a 2879, which is a 120 watt transistor, almost double the amount of drive, why do you want to have a voltage divider in there? There's no chance of you being able to overdrive the 4-pill section with a 2290 hitting it. 2290. Those are all matched transistors. I found a bunch of other little stuff, like the primary side of the transformers. The wires were heat shrinked, but not soldered. So they took the wires and they very carefully, very tightly wrapped them together, but they didn't shrink them. They just put solder on. They didn't solder them. They wrapped the wires together and then put shrink on them and left them. So we just maximized what we've got going on in here without getting wild. We increased the efficiency of the circuit, and that's where we're picking up our extra power. The main thing that allows us to pick up the power is the transformers, because now we have enough current in the power supply to let the amplifier run. So then I go and I put on the lid. Let's go talk about our fans. So these are VPPV, who cares? ADD, A, whatever, who gives a crap? But they are 12 volt fans, and they're 0.3 of an amp. Well, I hook up the lid, and they're like, barely turning. I'm like, what the hell? So I spin around, and I'm like, well, let's take a look at the bottom side of the lid. I'm like, oh, they got voltage regulators on them. I said, still, they should be turning a little bit faster than that. If we look really closely, it's illusion. The voltage regulator, the leads are tied together. The input and the output leads on the voltage regulator are tied together. Those parts are sitting there doing fuck all. And I'm like, well, then why is this thing turning so slow? Let's take a look at the resistor value. Brown, black, brown. They've got 100 ohm resistors on the ground lead. Each fan was seeing 4.42 volts. Barely turning. I'm like, okay, you got to meet me halfway here, world. Now, maybe the guy had him turned down at one point. He took this thing to WorldWide, or somebody took it to WorldWide and said, hey, man, this goddamn thing's so loud I can't even think next to it, which I can't see that even being a possibility now that I've increased the voltage to the fans. And so WorldWide went in there, bypassed the voltage regulators, and put a 100 ohm resistor in there and dropped it way down. I went and tied another resistor in parallel, which cuts our resistance in half. Okay, so now we got two 100 ohm resistors in parallel, and we're seeing 50 ohms of resistance. So now the fans are turning on 8.84 volts or 8.85 volts. Double the fans' rip'ems. The reason we did that is because once I was running it, I also did this modification before I fired it up. we added this block here. Now, the block does not cover up all the vents. We're doing that for a reason. The transformers are going to get warm too. They've got to be able to exhaust a little bit of air. So the main goal is to pressurize this enclosure, have air wrap around these parts, go down the length of the heatsink, and run out the back of the cabinet. When WorldWide put this together, he did a great thing. This is one homogeneous piece of heatsink from here to here. The whole distance of this thing from here to here is one giant hunky heatsink. The thing is, we figured out if you don't set the heatsink back just a hair, like maybe an inch, inch and a half from the back of the cabinet, there's no place for the air to recollimate. And what we mean by recollimate is the air molecules all move the same direction. When you put the heatsink directly up against the back of the cabinet, there's no way for that air to tumble and be able to flow out through the vent. It runs into a massive wall of pressure resistance. So it's like we're damned to do, we damned to don't. No, I don't have to go block up the hole that's normally over here on this side of the board, but in the same breath, we've got the heatsink directly up against the vent in the back. And since this is built from a older X-Force style cabinet, it's got slots in the back. So let's get in here and let's look at this for a second. That's our heatsink bed. So this whole top slot, worthless. So we got a little bit of space on our second slot and a little bit of space on our third slot. Now I'm going to call the customer and ask him if it's okay I cut this second rib out. I'd like to cut this first rib out as well. We'll find out. But with the fans turning really stupid slow, this thing had nothing but a choice of woo. I mean, as I famously said in one video when I was reviewing the new Texas Star fan kits, a warm fart from my dog's ass could move more air than what that thing was able to achieve with the fans set the way they were. Now, rest assured, brother, that just because we went up a couple volts in the fan and we went up a couple volts in the power supply, we're still insanely quiet. But we've got to get a little bit more air movement through the cabinet for this thing to last. At the end of the day, with 20 watts drive, that's seriously 20-25 watts worth of drive. So you take a 30 or 40 watt radio and run it into this thing, probably 30 watt. I wouldn't go any more than that because you're running up against that wall where you're going to overdrive the 2290 in peak envelope growth, not from the dead key standpoint. You're going to see more power than that. Everybody goes, oh my God, it's just another damn splatter box. It's Class C. Let's zoom on over here. So we're starting at 0 megahertz and we're looking all the way out to 500 megahertz. Splatter box my ass. Let's grow our signal a little bit more. Now we're starting to see a little bit of the second dBMs and third order dBMs. But those of us that know how to count will understand our reference line is all the way up at 0, and our second and our third order harmonics are 60 something dBs down. What is that? 45 dBm from our principal. No, that's not horrible. And a lot of that will get choked off at the antenna if the antenna is tuned properly. So the whole maybe 1.25 watts, 2 watts that thing's showing as output signal, no, is not massive signal separation. And then you got to remember that you're going to always have that little bit of a harmonic hump there at about 56, 58 megahertz, depending on how the crystal set is in the radio. That's a 400 watt carrier. We're still sitting above 16 volts. Massively improved our power supply. Okay, now, things that happen next. I'm going to put a body plug in the ground hole, and I'm going to clear the cabinet on the inside to keep it from corroding or having any further oxidization that takes place. which makes it easier for the next person that's got to work on it. If it's not me, it's somebody else, right? It's going to keep the board clean, and it's going to keep them from having to clean it. This amp is incredibly dirty on the outside. So I once had a friend of mine, his name was Hugh. I've told the story many times of me talking about learning how to, I'd go down and I'd work on his computer and thing, and he'd always tell me, BBI, he'd use my real name though, you know, when I take it to so-and-so and get him to work on it, it comes back, it's all clean. Well, he was a chain smoker, and it was gross. It's just gross. But what I learned from that is somebody's going to pay you good money to work on their stuff. At least you can do them the due diligence to take a rag and wipe off the outside. So I'm going to clear it, clean the outside of the cabinet up, and we'll be right back. I mean, all in all, this is actually a fairly well put together box. Just the technology in it was a little bit dated. I'm sure it was pristine and beautiful when it was new. And cleaned it up. It's ran for a long time. So we can't take anything away from it. I mean, we really can't. This thing's been here and done that. Got the t-shirt. Seen the girls at band camp. Whole 9 yards. I don't know if you know this, but WorldWide, the logo on WorldWide was blue. And it was so dirty when I started, it was brown. So we got the front of this box to clean up. Got all nice and pretty and shiny looking again. Went in here and painted everything. A little bit of clear. Now, I didn't mention this in the first hunk of the video, but I did scrub the transformers. And I scrubbed them last night, and I got about 80% of the rust off the outside of the transformers. Okay? Which is a lot. It was gross. Lack of a better term, just friggin' gross. So when we hit them with clear, I knew when I hit them with clear they'd make a radical visual change difference. They look like friggin' new now. New bridge, new power distribution network. Got this up to speed, cleaned up the fans on the bottom side, went in there and cleaned every single blade. Without me doing massive disassembly to the amplifier, I can't clean the top side. So I got in there and cleaned as best I could, cleaned around the guard, the grill. The lid's no longer brown, I can say that much. It's a much cleaner looking metal now. So let me move the camera here. I just want to show it to you from this perspective. And with a little bit of clear, it's going to look like that 10 years from now. Might be dusty, but hell, we've all got air compressors. Blow it out, go to work. You're not fighting through a whole layer of corrosion on the board. Okay, let me move the camera and put the lid on it, and then we're going to run it for max bird. It's like the never-ending story, man. I put labels on my stuff, and I was in a room the other night, and I was listening to some guys talk. They were debating me again, and they're still like confused on what the meters are that are in front of them, what they show. I was like, oh, they must have not watched anything here recently. This thing was just dirty. I mean, it wasn't bad. I've got amps that have been sitting over here that have been sitting for a long time that look worse, that are my own, so I'm no digging on nobody. Just saying it needed a little bit of paint. It needed to be cleaned up a little bit. Now the other thing I want you guys to see, and I got to get on video, is that this is clearly crowned down. That is a very common problem, incredibly common problem with having an iron core based power supply. One, they're very heavy, and two, the cabinets to which we're making them in is very thin. Now if we were using like an 1/8 inch thick aluminum or something a little bit heavier, we wouldn't have those kind of problems. But it makes shipping them very interesting. So the only way that we figured out how to get around this is we'll take a piece, and it's bowed. This is bowed. Turn my viewfinder around. It's bowed, okay? On both sides. So it's not a problem. The amp still sits flat when you sit it on a table because of the little rubber legs. We use foam core board, and we'll cut out a little square template for this thing to sit on. That's the only way to get them from being bowed that direction. Now, it gets bad when it gets bowed in, but the only other way, and nobody ever wants to pay for that shipping. The only other way is to put them in a very tight-fitting cardboard box, another incredibly tight-fitting cardboard box with a little bit of padding, and put them in a wood crate. And all you're doing is making it so that the thing is so heavy that the brown turd box kickers can't huck, chuck, puck it, and throw it. Okay. Let's turn on our peak kit. We're in 1X. So now what we've got hooked up is a derail radio. Okay? Click that into operate. Make sure our variable's all the way open. Wrong microphone. Right microphone. Okay. Click that into standby real quick. Let's show drive. Dials in water, 5-watt Silgan reverse. Okay. Hello. 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 A whole whopping 20 watts worth of drive. Whoop whoop. Okay. Hello. 500 bird. And you notice, if we listen to the pitch of the fans, they ain't slowing down. Hello, audio, 1, 2, hello, audio, 1, 2. So I've got to show that. I've got to show bird. This meter here. Because a lot of the older guys, they don't use peak kits. They don't believe in them. They think they're fanciful bullshit. I don't know. I just show it both ways. I don't let myself get caught up into that debate, that drama. I believe in peak, since we have radios now that are making the same amount of peak watts, completely different bird watts, and they're making the amps run completely differently. Amount of current the amp is drawing, like doubles. There's so many variables, so why not just show it both and people can get out of it whatever they want to take from it. It's simple, right? Well, I gotta say, Mr. N, your WorldWide's all cleaned up, internally and externally. Found a couple hundred more watts in your box, increased its efficiency. It is what it is. Well, gentlemen, I'm gonna run. I am gonna go and edit video for the next couple hours. It is Saturday after all. And I think I'm gonna put my giant 150 pound or 200 pound punching bag together today. I think that's what I'm gonna do. You guys have a good one. Big shout out to Siglant, big shout out to Excess Power, Bird, and Coaxial Dynamics. Thank you guys for letting me get to be here one more day working on this stuff, the sheet for you guys. I appreciate it. Got a bunch of major things happening at the end of this month. We're gonna have a bunch more fun projects for you guys to be able to get involved in here just very shortly. Appreciate you all. I'll see ya.